Hi friends, this is the 16th lecture in the lecture series for the preparation of GATE in mechanical engineering. Today we will be dealing with a concept called the radiation. Okay, we will be dealing with the radiation, and this radiation is nothing but a heat transfer phenomena or the type of heat transfer phenomena like the conduction and convection, and in this case the heat is transferred in the form of electromagnetic waves. Electromagnetic waves. So they are generally represented or they written as EM waves. Okay. So to describe the heat transfer, let's consider the first describe about the electromagnetic waves. So let's suppose this is a body at temperature T, and let's consider the electrons that are available at the surface of this particular body like this, and due to this temperature of this particular body, what happens is that the electrons that start oscillating about their mean position, and due to this emission or due to this oscillation, the get emitted electromagnetic waves emitted. Okay, and please note that the electromagnetic waves that emitted from this body will be having the wavelength in the range of 0 to infinity. And don't worry about the values, I just mentioned that it is having generally all the entire wavelength that are available. But in the radiation concept, within the realm of heat transfer, we are dealing with the thermal radiations which are having lambda, or the thermal radiations are the electromagnetic waves which are having the wavelength lambda within the range of 0.1 millimeter to 100 millimeter. So we will be dealing with the electromagnetic waves within the range of this particular 0.1 and 100 millimeter. Please note that this spectrum or this range is comprised of the entire visible region and entire IR region, and also a part of ultraviolet radiation region in the electromagnetic spectrum. Okay, these are from the spectrum. So that's about the thermal radiations, and we can plot this thermal radiation in two ways. That if we are plotting the thermal radiations like this, that is in the y-axis we are having the thermal radiation, and if you are considering the thermal radiations that emit from a particular body, and we know that the thermal radiations is having different wavelengths. So if we are plotting the thermal radiations of a body considering all the wavelengths, then we will be getting a graph like this. Okay, and this particular representation is called the spectral distribution. Okay, and if we are plotting the thermal radiations for a particular wavelength in all the directions in which that radiation is emitted or incident, or what happens, the energy emitted is will be like this, and this is also similar to the spectral distribution, and this distribution is called the directional distribution directional distribution. And the spectral distribution will give us the wavelengths that emitted from a particular body of the thermal radiation, and in the directional distribution we can find the direction with which the thermal radiation of a particular wavelength is emitted. Okay, so that's about the distribution of these thermal radiations. So before dealing with the heat transfer by radiation, we have to deal with certain terms associated with this particular case. So for that, let's consider the first term, that is nothing but the spectral emissive power. So to describe that, let's consider some surface like this, and for this surface, or rather for this surface, let's consider a unit surface area from the surface. This is unit area, this is unit area. Okay, so the spectral emissive power, which is nothing but the energy that is emitted from this unit area in unit time for a particular wavelength thermal radiation only. Okay, so that's why it is called the spectral emissive power. It is denoted as E lambda. So the spectral emissive power is nothing but the energy that emitted from a surface per unit area in unit time. Okay, that is nothing but the spectral emissive power. And there is also other term which is called the emissive power. And from this spectral emissive power, will be dealing with the emissive power, which is denoted by the letter E. So this E is nothing but the total energy that emitted from a surface per unit area in unit time, considering entire wavelengths of this particular thermal radiation or the energy. Okay, so this can be written as integral 0 to infinity E lambda d lambda. Okay, E lambda into d lambda. So this is nothing but the emissive power of a body. So the second term is nothing but the irradiation. Okay, and to describe that, let's consider some surface like this. So the previous case, and on this surface, let's consider a unit area. On the surface, and then the irradiation is nothing but the, or particularly spectral irradiation, which is given by the letter G lambda. So this irradiation is nothing but the energy that incident on a particular surface per unit area in unit time. Okay, if we are considering for a single wavelength thermal radiation, then the irradiation is called the spectral irradiation. And if we are considering entire wavelengths of the thermal radiation that incident on a particular body in unit area per unit area in unit time, then we will be dealing with the irradiation. Okay, so the emissive power is nothing but the total energy emitted per unit area in unit time. And for this spectral irradiation is nothing but the energy that incident on a surface per unit area in unit time. This is for a particular wavelength value lambda of the thermal radiation. And if you are considering the total energy that incident per unit area in unit time, then this will be the irradiation, and which is given by the letter G, and this is equal to integral 0 to infinity G lambda into D lambda, where G lambda is the spectral emissive power and the irradiation is given by the letter G. Okay, so next the third term, which is nothing but the spectral radiosity. Okay, so in a similar way that we described the irradiation and the emissive power, we can define this spectral emissive power, which is denoted by the letter J lambda, as the energy that emitted plus reflected. emitted plus reflected from a surface per unit area in unit time. Unit time is called the spectral spectral radiosity, and this if the spectral radiosity is for a particular lambda value of thermal radiation, and if we are considering the total energy that emitted plus reflected from a surface per unit area in unit time is nothing but the radiosity, and which is given as J is equal to 0 to infinity J lambda into D lambda. So please note these three equations. These three equations. Okay, so these are the emissive power and irradiation and the radiosity of a particular body. Okay, and if we describe this in a diagram, then consider some body like this, which is having the surfaces like this, and on this particular surface consider a unit area. On this unit area, the radiosity is nothing but the total energy that emitted plus reflected, that is emitted and reflected. Okay, so this is nothing but this is emitted and these are reflected and these are incident.